Now we can take the preceding back to the very beginning. If this is a graph of y equals 5 sine of theta, which is then raised 20 units to get the graph of y equals 5 sine of theta plus 20. To get the graph of y equals 5 sine of theta, we could have started with a circle of radius 5, constructed the graph. If we go all the way back to the very first principle, the idea that we start with a unit circle, and it's not always convenient. If you have big numbers here, 5,000 instead of 5, it's not convenient to try to visualize the unit circle, but in this case we can. So let's just think of where we are. We start with a unit circle. We use points around the unit circle, subdivide it, whatever. Identify theta with the arc distance around the circle, giving us the angle in radians. We construct the graph of just y equals plain old sine of theta. Then we use that graph, moving each point 5 times further from the y-axis to get the graph of y equals 5 sine of theta. So that y equals 5 sine of theta each point is 5 times I'll say this. Each point is 5 times further from the y-axis relative to y equals sine theta. So that should be fairly clear. This point, we have to take it 5 times further from the y-axis to get this point. This point here, we have to take it 5 times further from the y-axis to get the point lying directly above it. Then, of course, we move each point up 20 units to get this graph. So we start with our unit graph of y equals sine theta, and taking each point 5 times further from the, and I said from the y-axis, I should say from the theta axis. Taking each point 5 times further from the theta axis, we essentially stretch the graph in the vertical direction by a factor of 5. Now my statement, moving it 5 times further from the theta axis, and I would have to qualify that on the same side of the axis. So we don't take this point down here and move it 5 times further by moving it up here. Although that would satisfy the statement that we move it 5 times further, it's clear implicitly that we're going to move it on the same side of the axis. Okay, so if it's below the axis, it's going to move 5 times further below. If it's above the axis, it'll move 5 times further in the upward direction. That's called a vertical stretch. So we vertically stretch y equals sine theta by factor 5, then vertically shift (20 units in this case). Now we typically use the sine function and related trigonometric functions to model things that happen in the lab, out in the real world, theoretical ideas, and so forth. And as it occurs, the real world or the lab or whatever doesn't always fit with the simplest way of doing things, in the sense that there's no reason to expect that a sine function, whether down here or up here, will take its middle value at the time you start your timer, at the time you start your clock. Sometimes And in the majority of the time, that is not the case. The sine function might take its maximum value at theta equals 0. Okay, let's say that theta represents some function of t and theta is 0 when the time is 0. We're not going to worry too much about that now, but we'll get to that in a minute. That whatever theta represents, you can't necessarily assume that theta equals that your middle value of your sine function, the value between the low and the high values, the halfway between the low and the high values, occurs when theta equals 0. Okay, so let's just accept that for a moment, and we'll see some examples of how that can occur. Okay, so what if that doesn't happen, but you're still going through the same cycle of the sine function? Well, let's say that your value at theta equals 0 is a little higher. Let's say your value is here, and you want a nice sine function, but one that starts here when theta equals 0. Okay, well, you can accomplish that just by starting at a different point on the reference circle. You don't have to start at the positive x-axis. We'll do that in another video. But in terms of the graph, all you have to do to accommodate this, if you know that the function goes between 15 and 25, that the low and high values are 15 and 25, is you just take every point on the graph and shift it over this far. So what I've got is I've got a little arrow whose length is sufficient to take us from here to here. Now I apply that same arrow to a number of points on the graph. So I shift every point over to the left by the same amount. Now when I get down to a point here, I'm going to have to shift so that I go to the left of the x-axis, or the y-axis, I'm sorry, go into negative values of my horizontal quantity. And I continue doing that. Okay, I'm not going to draw as many of these, but you know, every point shifts over accordingly. Well, then what's my graph going to look like? It's going to look like something like this. So there's your graph shifted to the left. And of course, if we had an initial value down here, we'd have to maybe extend this graph into another cycle and shift it to the right. I'm not going to go through all the details of that, just giving you the idea that in addition to starting with our basic y equals sine of theta graph, we can vertically stretch it, we can shift it vertically, and we can shift it horizontally to get a meaningful model for something in the real world. And we'll talk a little bit more about what kind of model that might be in the next video.